Okay, well, last time we noted that we have collected some soundings across a transect which is down gradient from a wastewater lagoon. And what we want to do is determine in this area if any leachate from the lagoon has made its way down into this area, and whether it has possibly contaminated this reservoir. So we have a lot of background data on the site, and we know from the geologist tells us that we have a near surface layer. We have a well with a resistivity log, so we know what the background resistivities are in this particular area where the well was placed. No contamination was encountered, so we have basically the background resistivity of the uncontaminated aquifer. The aquifer is, the geologist also tells us that the aquifer is 20 meters thick, on average, and doesn't vary too much in this area. It's a fairly small area. This near-surface layer of clay is 10 meters thick, again, not too variable in thickness. And so down at about 30 meters, then, there's the aquifer is underlain by a layer of silt. And based on the resistivity log, the log analysis tells us that we have a clay with 20 ohm meter resistivity, an uncontaminated aquifer here with a resistivity of 100 ohm meters, and the resistivity of the underlying silt of 66.7 ohm meters. So this is a good opportunity to see if you can remember how to make these conversions from resistivity to conductivity. So take a couple minutes and give that a shot. You should have found that, well, remember what you do when you have a resistivity of 20 ohm meters. You want to figure out what the equivalent conductivity is. I mean, conductivity is just the reciprocal of resistivity, but the units change, and so we take the reciprocal here of this value, which is 1 over 20, which is 0.05. We multiply that times 1,000, which gives us 50. This is in units of millisiemens per meter. So we've gone from resistivities in ohm meters to conductivities in millisiemens per meter. And you should have got for 2166.7 ohm meters, you should have obtained 50, 10, and 15 millisiemens per meter for the conductivities. Okay, so we're just another reminder that when you see the data plotted here in IX1D, the individual data points for the horizontal dipole, the vertical dipole, the measurements of apparent conductivity are plotted at penetration depths, and these penetration depths aren't actual depths. The exploration depths that McNeil gave us were basically 1.5 times the intercoil spacing for the vertical dipole. You can kind of go back and review McNeil's technical note. But again, we just emphasize that these depths that are referred to as effective penetrations, don't correspond to actual depths of intervals in the subsurface. We can see on the solid lines are the apparent conductivities calculated from the model. The dots that we see here are those observations made in the survey. And we see that, these depths, we've got a depth of 10 meters here, 30 meters here, and there's really no clear, basically what you can tell from the data, both the horizontal and the vertical dipole measurements, is that the conductivity is dropping as you get deeper and deeper beneath the surface. So we don't really see the individual layers, and these penetration depths don't refer to boundaries in any way. So just another reminder of that. You can download the IX1D demo version of the program, as we mentioned before. And if you actually wanted to play around with the data, this is the data that we're using here. Notice that the EM31, we have vertical and horizontal dipole measurements. It's for the 3.66, 3.67 meter intercoil spacing, and at these 6 different locations along the profile. Just flip back up here quickly for a reference. We have 6 soundings, and the data that we're presenting here is for 6 soundings for a full set of 8 measurements for the EM31 and the EM34, 10, 20, 40 meter intercoil spacings. So if you had this in a file, you would go over here to File and Open, and you'd bring in your data. You might have a starting model that would look something like this. And you can see that the calculations don't quite match the observations. So there's something else going on here in the model, and that would be, that would be the purpose of your modeling exercise, would be to get a match between the calculations and the observations. So we have the geologist has given us a resistivity log from the site. So we know that there's a 3rd layer down here. We know that there's a silt layer here, and if we put that silt layer in, if we use the resistivities that were obtained, or the conductivities that were obtained from the from the well log, we see that we get an excellent match here, and that the aquifer is uncontaminated. So if we go away from that site, which we know is uncontaminated, just based on the well log response, and we want to evaluate the possibility of whether or not there's a contaminated zone in the aquifer, then we're going to have to add a layer. So this is how it works in IX1D. We put in the conductivities. So we know what the conductivity is of the overlying clay, the freshwater aquifer, the uncontaminated aquifer, and the underlying silt. We go ahead and put in those values, but we divide the aquifer up into 2 intervals. We assume that the contamination is drifting down, or that it's a light non-aqueous phase contamination, or that it's kind of making its way down. It's settling down into the base of the aquifer. So to make this exercise simple, we're assuming that the contamination is in the upper part of the aquifer. We also put the depths in there. We know from the log that the upper clay layer is about 10 meters thick. The aquifer is 20 meters 20 meters thick, so it extends down to 30 meters. The silt, well, we don't know where its base is. So what we do is we put in conductivities of 50, 10, 10, and 15, and we put in thicknesses of 10, 10, and 10. And after one forward calculation, we see that we don't quite have a match yet. And again, just to kind of zero in, then after a second iteration, we have a better match. Just to remind you of the model here, this is the near surface clay interval, this is the contaminated aquifer, this is the uncontaminated aquifer, and this is the silt lying at the base of the aquifer. We've fixed these parameters. We allowed the conductivity of the contaminated aquifer to vary, and we see that it has a conductivity, the contaminated zone has a conductivity about 10 times that of the uncontaminated portion, around 100 millisiemens per meter. Its thickness is 20.06 meters. That's a little bit too thick. The geologist tells us that the aquifer is 20 meters thick, so the base of the aquifer should be up here. Can we make that work? Also, we have to fix this upper layer. We can't really fix these 2 layers because we don't know. and that's why we leave them unfixed when we go through the first forward inversion and then iterations, either one at a time or multiple iterations. So we've kind of mentioned that fixing and freeing is important when you're developing your model, when you're trying to get a good match between the calculations and the observations. And fixing and freeing is important because you want the model to be consistent, to remain consistent with what you know about the geology. So we know that the upper layer has a conductivity of 50 millisiemens per meter. We know that the uncontaminated aquifer has a conductivity of 10 millisiemens per meter, and the underlying silt 15 millisiemens per meter. So we just fix all those numbers. The geophysical log tells us that we can do this. This is kind of in the ballpark. We also know that the silt has a thickness of 10 meters, and it's fairly a layer of uniform thickness throughout the area. So we're also fixing that. And that's about all we can fix here. So we have all these fixed parameters to start us off, and then after we go through the inversion, these initial starting parameters are modified by the program to give us a good match between the observations and the calculations. Now, if we come back here, and before we get a perfect match, and that's pretty easy to do when you're working with model data. When you're working with real data, that's not always possible. You don't always get, really small error, which is less than 1% here. I didn't include the error in this case. But if you leave some error in your inversion, and then you use the analyze equivalence tool here in the software, you have to do at least one iteration, and then you can analyze equivalent solutions. You'll see here that we have these dashed lines in here, which tell us something about the different possible models that you could have, all of which would give you a similar level of error. So we've talked about, non-uniqueness is something that you talk about in geophysics a lot. Because your solutions are always non-unique, there are other ways to give you exactly the same result, different models to give you exactly the same result. And here, with the equivalent solutions, we're seeing some of the variety. So if you're talking to a client, you go through this exercise of collecting all the data, developing the models. You want to give them some sense of the variability that you could have in the thickness of the contaminated portion of the aquifer, and so that's the main objective of the work. And these equivalent solutions allow you to do that. And we're going to talk more about that next time. So hope to see you then.